This video demonstrates Sentinel, a tool to understand data system behavior and performance. Understanding the performance of modern applications and the databases that support them is extremely difficult. Both systems contain a large number of components and features that play a significant role in system performance. Furthermore, these systems are tightly coupled. The performance of the application depends on that of the database, and the performance of the database ultimately depends on what queries the application is issuing. Therefore, we need to consider the behavior of both systems when we address performance problems. Understanding system performance is difficult at the best of times, but it becomes even more critical when system performance is impaired. Poor performance leads to unhappy customers, and unhappy customers lead to losses in revenue. Ultimately, this impacts a company's bottom line. Our system, Sentinel, addresses this problem by providing deep insight into system behavior without requiring large code changes or significantly degrading system performance. These insights enable administrators to both understand and remedy issues in system performance. Let's see an example of how this works. In our first demonstration, we use Sentinel to investigate a performance degradation in an application by comparing the current workload, shown in green, to a baseline workload, shown in brown. The top left panel presents the largest differences in terms of proportional event frequency between the two workloads. Events refers to important happenings in system behavior as the system processes user requests. Sentinel extracts these events by intercepting logging calls, as we'll describe later. We see that the baseline workload has more events of all of these types compared to the current workload, which highlights the extent of the performance problem. These top panels present the largest time differences to transition from one system event to another. Immediately, the leftmost CDF stands out. This CDF highlights differences in execution time for the buy confirm transaction. Clicking on the graph reveals more details in the panes below. This middle pane shows which events transition to and from the event of interest in the current workload. The right pane shows the same, but for the baseline workload. These edges show the probabilities of what event will happen next, given that the previous event has just occurred. We refer to them as transition probabilities between events. Clicking on the source code button brings up the source code for the clients that drive the workloads, centering it on the event of interest. Given our analysis, we can conclude that the buy confirm transaction is taking longer to execute in the current workload, which affects the performance of the workload as a whole. To locate the root cause behind this performance degradation, we'll use Sentinel to investigate the behavior of the database as well. We observe that there are more locking-related events in the current workload. Viewing the transition time differences for the locking events reveals that there is a large difference in lock acquisition time between the two workloads. Given this difference, and the difference in event counts, we can conclude that the problem is lock contention, which heavily affects the buy confirm transaction. Now, we'll describe how Sentinel provides these insights in detail. Developers use debug logging to audit their systems and to remedy any issues that occur. Debug log messages describe system events, for example, when a lock is acquired or released. As the system runs, these debug log messages are written to a file for offline analysis. Unfortunately, debug logging is known to impair performance, so developers often only log coarse-grained messages to disk, discarding the more fine-grained messages to avoid this performance degradation. Our system, Sentinel, intercepts these logging calls and uses them to update its in-memory models that describe system behavior. In doing so, Sentinel can capture log messages of all granularities and use them to update its models without incurring the overheads of writing them to file. Furthermore, updating these models avoids contention by design, which further limits Sentinel's overhead on the system. Afterward, Sentinel passes the log message along to the log library for the usual processing. Sentinel's in-memory models are extracted and then stored in a model database for later comparisons. By storing models according to different workloads and system configurations, Sentinel enables comparisons between them, enabling users to understand their effects on performance and system behavior. Sentinel compares these models according to 3 dimensions: event proportion, transition probabilities between events, and the time to transition between events. These differences are ranked by their size, and then available via either the UI that we've shown earlier, or an API. By ranking these differences along the 3 dimensions, Sentinel captures complex behavioral differences between system configurations and workloads, as we will see in our next demonstration. In our next demonstration, we use Sentinel to investigate a current workload whose behavior has shifted significantly from the expected baseline workload. Therefore, it exhibits significantly different behavioral characteristics and performance. This time, the top left panel indicates that the new products and get bestsellers transactions are more popular in the current workload compared to in the baseline workload. However, transactions like buy request, customer registration, and buy confirm are more popular in the baseline workload, which suggests that it may be more update intensive compared to the current workload. To investigate, we click on the bestsellers transaction, which brings up more details in the panes below. We see that the probability of transitioning from the home page transaction to the bestsellers transaction is much higher in the current workload compared to in the baseline workload, an important difference in application behavior. Clicking on an edge brings up a CDF of the transition times between the relevant events. The CDF for bestseller transaction latency is similar for both workloads. However, we note that it takes around 200 milliseconds to execute in most cases. By contrast, the buy request transaction, which is popular in the baseline workload, takes only 2 milliseconds to execute. This tells us that transactions that are popular in the current workload take longer to execute than those popular in the baseline workload. In turn, this leads to lower application performance overall. Now, we'll relate these differences in application behavior to differences in Postgres behavior. We note that there are many more query processing events in the baseline workload compared to in the current workload, which is correlated with query throughput. Counterintuitively, there are many more lock-wait events in the baseline workload compared to in the current workload, despite the current workload's poor performance. However, we note that there are more disk writes, or storage manager writes, in the baseline workload compared to the current workload, which attests to its more update-intensive nature. Similarly, we can ascribe these differences in lock intention to differences in the update intensity of the workloads. Next, let's examine differences in the transition time CDFs. This 100 millisecond step-like difference in transition time is odd, so we use the transition graph to bring up the relevant checkpointer source code. We search the code for 100 milliseconds. Examining the code reveals that this 100 millisecond difference occurs because the checkpointing process can be throttled when there are fewer pages that need to be written to disk. This is more often the case under the less write-intensive current workload. The middle CDF shows the effects of lock intention on the baseline workload, which aligns with our discussion from earlier. Finally, the tail of the third CDF shows increased disk read times for the current workload compared to baseline. Sentinel surfaced important information regarding the performance of transaction and query execution in both the application and the database. This information will direct the analyst to improve the performance of the slow bestsellers transaction, which is popular in the current workload. It is important to note that because Sentinel integrates directly with debug logging, its insights are available to all systems that use it, with very low overhead. For more details, please see the accompanying paper.